In this lecture, we will see design of columns. A column is a structural element that is predominantly subjected to axial compressive forces. When a compression member is vertical, it is called column, and when it is horizontal or inclined, it is called strut. The main difference between column and a strut is both are compression member, whereas your column is vertical, your strut is horizontal or inclined. So this is horizontal or inclined. So as per IS 456-2000, page number 41, clause 25.1.1, the code defines a column as a compression member having effective length greater than 3 times its least lateral dimension. So as per this clause, so let me open the code, page number 41. So IS 456, page number 41. See here, compression members definition 25.1.1, column or a strut is a compression member the effective length of which exceeds 3 times the least lateral dimension, which means the ratio of effective length to least lateral dimension. If this ratio is greater than 3, then it is treated as column. If this ratio is less than 3, then it is pedestal. For example, in a rectangular column, you have size 300 by 400 mm rectangular column. The least lateral dimension is 300 mm. So this will be your least lateral dimension. So effective length to least lateral dimension ratio, if it is greater than 3, then it is column. If this ratio is less than 3, then it will be a pedestal. So according to this code clause IS 456-2000, clause number 25.1.1. Next we shall see classification of columns. Classification. So first type of classification will be based on cross section. Based on cross section, the columns may be rectangle, square, circular, or it may be T-shaped column, L shape, or sometimes plus shape, and hexagonal. So this is classification based on cross section of the column. So you have seen, many of you have seen rectangle, square and circular columns. So these two are widely used in case of high-rise structures, T shape and L shape columns. Okay. So this is first classification is based on cross section. So second type of classification is based on type of loading. So based on type of loading, so columns are categorized into three. One is columns with axial loading. Axial columns. Second one is columns with uniaxial eccentricity. So third one will be columns with biaxial eccentricity. Okay, this is based on type of loading: axial columns, uniaxial and biaxial. So next, third type will be based on slenderness ratio. Based on slenderness ratio, columns are categorized into short column, and slender columns. So slender columns are nothing but long columns. So these short columns will fail in compression, axial compression, whereas this long columns will fail due to buckling. Buckling or bending. So next classification will be based on type of reinforcement. So type of reinforcement. So first one will be tied columns, spiral columns and composite columns. So this is the brief introduction about column definition and classification of columns. So first classification is based on cross section. Second classification will be based on type of loading. Next, third one will be based on slenderness ratio. Fourth will be based on type of reinforcement. So after the classification, so next thing is beams and slabs for flexural elements. I think you remember. Beams and slabs are flexural members. So steel will be provided to resist bending moment and shear force. So in beams and slabs, steel will be provided to resist bending moment and shear force. So in case of columns, in addition to axial compressive load, it has to resist biaxial moments. So columns are designed for axial compressive load and biaxial moments. Okay. So this I clearly explained in ETABS while defining your section properties. See here. Where is open board? Yes. See, once you open ETABS, in case of define section property, frame section, in case of beams, you go to modify. In case of reinforcement, you click on modify. See here. Your beams are designed to resist bending moment and shear force. Okay. Whereas your columns, so you can check with the column property. So column, modify, you click on modify reinforcement. See here, your columns are designed for axial load and biaxial moments. So that is P, M2, M3. So P is axial load, M2 and M3 are biaxial moments. Okay. So next, so columns are designed for 3 actions. So columns are designed for 3 actions. That is PMM. P is for axial force and these M refers to biaxial moments. Okay. So assume if I have a column like this, so this is the cross section of the column. So this is your axis 3, 3 and this is your local axis 2, 2. So width of the column is B, whereas depth of the column is D. So this is width width of the column B, whereas depth of the column is D. So assume this is quadrant 1, this is quadrant 2, and this is quadrant 3, and this is quadrant 4. So column is subjected to 3 actions. So P, M2, M3. So P is axial force, M2 is this one, moment about 2 axis, M3 it is like this. So this is M3 and this is M2. So because of M2, so I will change the direction. So I will take this direction, M2. Okay, no problem. Let it have the old direction. So M2. So this is your M2 and this is your M3. So because of M2, so quadrant 2 and 4 are subjected to compression. Okay. So because of M3, so quadrant 1 and 2, quadrant 1 and 2 are subjected to compression. Okay. So whereas P, it will cause compression in quadrant 1, compression in quadrant 2, compression in quadrant 3 and compression in quadrant 4. Okay. So overall strain profile in column cross section is very complex. It all depends upon PU and M2, M3. So complex behaviors because of 3 actions interacting each other. So overall strain profile in column is very complex. It depends upon 3 interactions. So in case of columns, calculating the capacity of column is not simple as in the case of beams. In case, you can easily calculate the capacity. So you have the ready formulas. Mu limit equals 0.133 FCK BD square. So this is, by using these equations, you can calculate the capacity of beams. So calculating the capacity of columns is not simple as in the case of beams. So for calculating the column capacities, we make interaction diagrams. We make interaction diagrams, or we call it as PM curves. PM curves, or sometimes we call it as interaction capacity curve. Interaction capacity curve. So these are used to find the column capacities. Okay. The column design will be carried out on 2 steps. Calculating column capacities, we make interaction diagram and calculating design moments. So column design will be carried out on two steps. One is calculating design moments. First step is calculating design moments. So second step is calculating column capacities. Calculating column capacities. So you always remember, column design will be carried out on two steps. So this is your first step, calculating design moments. So second step is calculating column capacities. Okay, so ETABS will calculate these two, interaction diagrams as well as design moments. So while in case of manual design, you need to refer SP16 for column capacities. So there are charts 27 to 38 are used for rectangular columns with reinforcement on two sides. So next, charts 39 to 50. Charts 39 to 50 are for rectangular columns with reinforcement on four sides. So charts 51 to 62 are for circular columns. Okay, so these charts have been prepared for three grades of steel. So that is for Fe 250, Fe 415 and Fe 500, and for four values of cover ratio. So that is, cover ratio means D dash by D. So 0.05, 0.10, 0.15 and 0.20. Okay, so these charts 27 to 62 have been prepared for three grades of steel: 250, 415, 500. So with four values of cover ratio, so that is D dash by D, that is 0.05, 0.10, 0.15, 0.20. So if you open SP16, so charts 27, see here, chart 27, compression with bending rectangular section distributed equally on two sides. So this is for Fy 250 and cover ratio 0.05. So chart 27 to 38 for rectangular columns with reinforcement on two sides, whereas charts 39 to 50 are for rectangular columns with reinforcement on four sides. So charts 51 to 62 are for circular columns. So these charts are nothing but interaction diagrams. Okay. So these are the basics you should remember before going to manual design of columns. So next we shall take up one problem on column design. So first, column size 300 by 500 mm. So your grade of concrete M25 Newton per mm square. So your grade of steel 500 Newton per mm square. So for columns clear cover it is 40 mm. So you have PU, so analysis moments 300 kilonewton, and MU33 40 kilonewton meter, MU22 10 kilonewton meter, floor to floor height it is 4.5 meter. So we have beam depth 400 millimeter. So let me have the column cross section. So this is the cross section of column. So total depth D, so it will be 500 millimeter. So width it will be 300 millimeter. So this is your local axis 3 and this is your axis 2, same as in ETABS. See here. So horizontal is 3, vertical is 2. Okay. So MU33. So MU33 moment about 3 it is 40 kilonewton meters, whereas MU22, so this MU22 it is 10 kilonewton meters. So as I told in the beginning, column design will be carried out on 2 steps. So first step will be calculation of design moments. First step will be calculation of design moments. Okay. So let me divide the page. So divide page like this into two columns. So first, so this column is about 3 3, and this is about 2 2. See here, from this diagram, so for mu33, which is the depth resisting mu33, so this 500 will resist mu33. Okay. For mu22, depth will be this side, so 300. So here about 3 3, so width 300 millimeter, depth will be 500 millimeter. So about 2 2, width 500, so depth 300 millimeters. So first is moments due to minimum eccentricity. Moments due to minimum eccentricity. So if you refer IS 456 2000, page number 99, clause 25.4. So you have the formula for moments due to minimum eccentricity. So let me open the code IS 456 first, page number 99. So clause 25.4, let me find the clause. So clause number 25.4. Yes, here. Clause number 25.4. So moments due to minimum eccentricity. Yes. Yes. So 25.4. I think this is page number 42. Sorry. So this is on page number not 99. So this is page number 42. So you have the formula minimum eccentricity. All columns shall be designed for minimum eccentricity equal to the unsupported length of column divided by 500 plus lateral dimension divided by 30 subjected to a minimum of 20 mm. So, okay. So let me copy the formula. So minimum eccentricity E minimum equals L unsupported divided by 500 plus D by 30. Okay. So E minimum equals, so L unsupported. See here, floor to floor height is 4,500, which means 4.5 meter. Your beam depth is 0.4 meter, so which will be 400 millimeter. So your L unsupported length will be 4.5 minus 0.4. So it will be 4.1 meters. So 4,100 divided by 500 plus D. So about 3 depth will be 500. 500 divided by 30. So 4,100 divided by 500 plus 500 divided by 30. So it will be 24.86. So 24.86 millimeter, which is greater than 20 mm. So here about 2 E minimum equals L unsupported So divided by 500 plus D divided by 30. So 4100 divided by 500 plus here D. For 2 axis D will be 300. So 300 divided by 30. So 4100 divided by 500 plus 300 divided by 30. So it will be 18.2. 18.22 millimeter, which is less than 20 mm. So this is eccentricity. So moments due to minimum eccentricity equals, so Pu multiplied by minimum eccentricity. So Pu is 300 into 10 power 3 Newton multiplied by minimum eccentricity. It is 24.86 or 87. So which will be, so 300 into 10 power 3 multiplied by 24.86. So which will be 7.45. So this is in millimeter. So final answer is 7.45 into 10 power 6. 7.45 into 10 power 6 Newton millimeter. So if you divide this by 10 power 6, so it will be converted to 7.5 kilonewton meter. So this is your moments due to minimum eccentricity, about 33. So this is about 33. Similarly about 22. So minimum eccentricity moment equals Pu multiplied by E minimum. So which is equal to, your Pu is 300 into 10 power 3 Newton multiplied by here eccentricity. So eccentricity is less than 20 mm. So you need to consider minimum. The code says minimum you should have 20 mm eccentricity. So which will be 6 into 10 power 6 Newton millimeter. So moments due to minimum eccentricity will be 6 kilonewton meter. So let me calculate it. So 300 into 10 power 3 into 20. So 6 into 10 power 6. Okay. So this is moments due to minimum eccentricity. So this is moments due to minimum eccentricity. So in the next step, so next step is moments due to slenderness effect. So second will be moments due to slenderness effect. So for which same you have two axes, about 3 3 So this is about 2 2. Okay. So for which you refer IS 456 2000, page number 41, clause 25.1.2. So clause, page number 41, 25.1.2. See this one. Short and slender compression members. A compression member may be considered as short when both the slenderness ratios Lex divided by D and Ley divided by are less than 12. Okay. So what is the formula? So slenderness ratio lambda equals L effective divided by D. Okay. So L effective, so which will be calculated as K multiplied by L unsupported. So L effective equals K multiplied by L unsupported. So K, I will take it as 1. L unsupported, you calculated, I think it is 4.1. So L effective, so 1 into 4.1, so it is 4.1 meters. So here in the calculation, 4100 divided by, so depth will be 500. So 4100 divided by 500. So here it is 8.2. 8.2, which is less than 12. What the code says, when both ratios are less than 12, then it is called as short column. So here the ratio is 8.2 less than 12. So you can take this as short column. So no slenderness effect. So no slenderness effect. No additional moment is required. No additional moment. So here about 2 to axis, your column is short column. So no slenderness effect. So no additional moment is required. So about 2 to, so lambda equals L effective divided by D. So effective length 4100, depth will be 300. So 4100 divided by 300. So it will be 13.6. So which is greater than 12. So we can say column is slender about 2 to axis. Additional moment required. Additional moment required. So we need to calculate the additional moment. So additional moment is calculated as additional moment. So MA22 equals PUD divided by 2000 into lambda square. So this formula it is in page number 71, clause 39.7.1. So page number 71, see here. So this is the clause for additional moment. Okay. So I will copy the formula. So here PUD divided by 2000 into LEX by D whole square. So LEX by D can be written as lambda. Okay. So here PU is 300 axial load, depth will be 0.3. So about 2 axis, so depth will be 300 millimeter, so which will be 0.3 meters. So 0.3 divided by 2000 into lambda 13.6 square. So your additional moment will be, so PU 300 multiplied by 0.3 divided by 2000 multiplied by 13.6 square. So your additional moment is 8.32. So MA22 additional moment is 8.32 kilonewton meter. So here no slenderness effect, no additional moment is required. So here about 2 additional moment is required. Okay. So next, will be final design moments. Final design moments. So this axis is 3 and this axis is 2. So first your analysis moment. Analysis moment about 3 axis is 40 kilonewton meter. So moments due to minimum eccentricity, so which will be 7.5 kilonewton meter. So next, moments due to slenderness. Moments due to slenderness, so which will be 0. So this is about 3. So similarly about 2. So analysis moment is 10 kilonewton meter. Moments due to minimum eccentricity 6 kilonewton meter. Moments due to slenderness effect 8.32 kilonewton meter. So let me recall the values. So your analysis moment about 3 3 is 40. So moments due to minimum eccentricity 7.5. So here no additional moment required. Here it is 0. So 47.5 0. So 47.5 0. It is about 3 3. So similarly for 2 2. So for 2 2 analysis moment is 10. So minimum eccentricity moment 6. Slenderness moments due to slenderness effect 8.32. So about to 2 to 10 6 8.32. So 10 6 8.32. Okay. So final design moments equals maximum of 1 and 2 plus 3. So here also same. Final design moment maximum of 1 and 2 plus 3. So maximum of 1 and 2. So maximum is 40 plus 3 is 0. So your design moment remains 40 kilonewton meter. So this is MU33. So here, so maximum of 1 and 2, 10 plus 3 means 8.32. So 18.32 kilonewton meter. So it is MU22. Whereas your PU is 300 kilonewton. So these are your design moments. So this is the first step in column design. So calculation of design moments. So next, second step. So this is the first step, calculation of design moments. So second step will be column capacities. So column capacities. So this is about 3 3 and this is about 2 2 axis. So for 3 3 axis, B will be 300 mm and D will be 500 mm. Here B 500 mm whereas D 300 mm. So first you calculate D dash. So which means clear cover 40, 8 mm dia stirrups, your main reinforcement. If it is 16, 16 by 2. So D dash. So 40 plus 8 plus 8. It is 56. So 56 millimeter. About this axis also 56 millimeters. So next D dash by D. So D dash is 56 divided by D 500. Okay. So 56 divided by 500. So which will be 0.112. 0.112. So higher value, next value is 0.15. So here d dash by d. So d dash 56, d 300. So 56 divided by 300. So it will be 0.186. 0.186. So next higher value 0.2. So next I will assume PT, percentage of steel, as 1.6%. So on both axis I will assume 1.6 PT. So next calculate PT by FCK value. So your PT is 1.6. So your grade of concrete is 25. So 1.6 divided by 25. 1.6 divided by 25. So which will be 0.064. So which will be 0.06. So here also PT by FCK will remain same, 0.06. So in the next step, you calculate PU divided by FCK BD. So your PU is 300 into 10 power 3 divided by grade of concrete 25, B 300, D 500. So it will be 300 into 10 power 3 divided by 25 into 300 into 500, 0.08. 0.08. So about this axis also, PU divided by FCK BD equals. So it will remain same, 0.08. Okay. So let me list the values. So PT by FCK, here it is 0.06. Here also PT by FCK 0.06. Okay. PU divided by FCK BD, it is 0.08. PU divided by FCK BD, 0.08. And D dash by D, D dash by D 0.15. So here it is D dash by D 0.2. Okay. So you open SP16. SP16 chart number 49. Chart number 49. So this is the chart. So here grade of steel 500 Newton per mm square, D dash by D 0.15. Okay. See here. You know the value of PT by FCK. It is 0. This curve. 0.06 PT by FCK. So 0.06. and you know the value of PU by FCKBD. PU by FCKBD 0.08. So it is 0.08. So this axis, y axis, PU by FCKBD. So it is 0.08. So somewhere here. Okay. So you will get on the x-axis. On the x-axis you have mu by FCKBD square. So this is your 0.06 curve. So you will get mu by FCKBD square. So mu, this is 33 divided by FCK BD square. So it is 0.1. So similarly, so this is chart number 49. For this axis, you refer chart 49. For this axis, you refer chart 50. Based on this d dash by d value, pt by fck and pu by fck bd value, you extract mu33 by fck bd square. Here it is 0.1. For this axis, mu22 divided by fck bd square, which will be almost 0.09. Okay. So mu33, your FCK is 25 into B 300 into depth 500 square equals 0.1. So here mu22 divided by 25 into 300 into 500 square. So it will be 0.09. So 25 into 300 into 500 square multiplied by 0.1. So 187.5. So here about this axis, so MC33, so capacity along 33 direction or about 33 direction, it is 187.5 kilonewton meters. Similarly, for 2 it is 25 into 300 into 500 square multiplied by 0.09. So it will be, so sorry, here depth will change. So here B is 500, this depth is 300. So 25 into 500 into 300 square. So into 0.09. So which will be 101.25. So this is MC22, 101.25 kilonewton meter. So if you observe this value, so MC33, which is greater than mu33, so this MC22, which is greater than mu22. So MC33, it is 187.5 kilonewton meter, which is greater than mu33. So design moment along 33 action, 33 direction, it is 40. So it is 40 kilonewton meter. So here MC33 101.25 kilonewton meter. So Mu22, so design moment along 22, it is 18.32. So which will be greater than 18.32 kilonewton meter. So hence this is satisfied. So it is uniaxial moment capacity of the section about 33 and 22 axis. So this step is nothing but uniaxial moment capacity of the section about 33 and 22 axis. Okay. So next, in the next step, we shall calculate interaction ratio. So next step will be interaction ratio or interaction check. So we have the formula Mu33, which will be design moment, divided by MC33, okay, your capacity. So power alpha n plus Mu22, your design moment, divided by MC22 capacity, power alpha n. This should be less than 1. Okay. So this formula, it is in IS 456 clause 39.6. You have this formula. So first you calculate alpha n. It is Pu divided by Puz. So here alpha n equals Pu divided by Puz. So first you need Puz. So Puz is 0.45 FCK AC, area of concrete, plus 0.75 multiplied by Fy multiplied by ASC, so area of steel. So 0.45 multiplied by FCK 25, AC area of concrete, so it will be 300 multiplied by 500 area of column, in which you remove area of steel. So for 1.6% of gross, so your column is 300 by 500, you will get 2400 mm square. So you will get area of steel around 2400 mm square. Okay. So plus 0.75 into Fy. Fy is 500 multiplied by ASC, area of steel, again it is 2400. So 0.45 multiplied by 25 multiplied by 300 multiplied by 500 minus 2400. So plus 0.75 into 500 into 2400. Okay, so this is in Newton. You divide this by 1000, you will get it in kilonewton. So it is 2585.1. So your PUZ will be 2585 kilonewton. So PU by PUZ value, PU is 300 kilonewton. So it is 2585 kilonewton. Okay. So 300 divided by 2585. So it will be 0.11. So 0.116. Okay, which is less than 0.2. You remember it is less than 0.2. So if you open the code IS456, so clause 39.6. See here. For P values of PU divided by PUZ 0.2 to 0.8, the values of alpha n vary linearly from 1 to 2. Okay, for values less than 0.2, alpha n is 1. For values greater than 0.8, alpha n is 2. So here in our case, so alpha n is 0.116. Okay, so which is less than 0.2. So alpha n is 1. So you can directly write here. So your alpha n will be 1. So if you substitute all the values in this equation, so design moment divided by capacity about 33 power alpha n plus design moment divided by capacity of moment about 22 power alpha n. This interaction ratio should come less than 1. So design moment is 40 divided by capacity is 187.5 power alpha n 1 plus about 22 design moment is 18.32 divided by capacity is 101.25 power 1. So let me check this. So 40 divided by 187.5. So power 1 plus 18.32 divided by 101.25. So power 1. So it will be 0.39. So this is 0.39. So which will be less than 1. So then the whatever the column, it is sufficient. The size is also sufficient, 300 by 500, and whatever the reinforcement you assumed PT 1.6%, it is also correct until this ratio should be less than 1. If this ratio, if it is greater than 1, then you need to increase column size, or you can increase percentage of steel. Okay. So column design will be done on two steps. See here. First step is calculating the design moments. Second step is calculating column capacities. So percentage of steel PT, it is 1.6%. We will get AST of 2400 mm square. So let me check this. So your PT is 1.6 divided by 100 multiplied by column dimensions 300 into 500. So it is 2400 mm square. So we will check maximum and minimum longitudinal reinforcement. Okay. So minimum percentage of steel will be 0.8% of gross cross-sectional area. So which will be 0.8 divided by 100 into 300 into 500. So minimum area of steel it will be, so 0.8 divided by 100 multiplied by 300 multiplied by 500. So it will be 1200. So 1200 mm square. So this is the minimum. So maximum, I think these clauses are provided in IS 456, page number 48, clause 26.5.3.1. So let me open the code, page number 48. See here, 26.5.3.1 longitudinal reinforcement. The cross-sectional area of longitudinal reinforcement shall not be less than 0.8% nor more than 6% of the gross cross-sectional area of the column. So minimum is 0.8%, maximum is 6%. But to avoid congestion of reinforcement, the code restricted 6 to 4%. So when the bars from the columns below have to be lapped with those in the columns under consideration, the percentage of steel shall usually not exceed 4%. So maximum percent is 4. So PT max, so it will be 4% of gross cross-sectional area. So 4 divided by 100 multiplied by 300 multiplied by 500. So which will be, so 4 divided by 100 multiplied by 300 multiplied by 500. So it will be 6000 mm square. So minimum area of steel it is 1200, maximum 6000. So my provided steel is 2400. So it is more than the minimum and less than the maximum value. Okay. So what about the shear reinforcement? So shear reinforcement. So for pitch and diameter of lateral ties. So you refer IS 456 2000, page number 49, clause 26.5.1.8. So let me open page number 49. See here. Pitch and the diameter of lateral ties. First we shall check the diameter. So diameter, the diameter of the polygonal links or lateral ties shall not be less than 1/4 of the diameter of the largest longitudinal bar, and in no case shall less than 16 mm. Okay. So what the code says, not less than 1/4 of the diameter of the largest longitudinal bar. So 1/4 times 16. Okay, it should not be less than 1/4 16 times. So 1/4 into 16, which means 4 mm diameter of lateral ties. Anyway, we will be providing 8 mm dia. For lateral ties, we will be providing 8 mm dia. So next, spacing. Next it will be spacing. See here. The pitch of transverse reinforcement shall be not more than the least of the following distances. First one will be the least lateral dimension of the compression member. Second one will be 16 times the smallest diameter of the longitudinal reinforcement bar to be tied. Third one will be 300 mm. So first one will be the least lateral dimension. So your column size is 300 by 500 mm. So least lateral dimension is 300 mm. So second one, 16 times the smallest diameter of the longitudinal bar. So 16 into longitudinal bars, I used 16 mm. 16 or 12. Okay, I will go with the 12 mm. So assume if I provided 12 mm, or let me check in the calculation. So in calculating d dash by d, I used 16 mm. So let it be 16 mm. So 16 times 16. So 16 multiplied by 16, which will be 256. 256 mm. So last third one will be 300 mm. So code says should not be more than the least of the following distances. Again, so again you need to provide least. So least value is 256. So you can provide 8 mm dia ties at 250 mm center to center. So main reinforcement. So PT equals 1.6%. So 1.6 means 1.6. So area of steel, it is 2400 divided by, if you provide 16 number of bars, it will be 12 numbers. So main reinforcement will be 12 numbers of 16 mm dia. So this is the final reinforcement. Okay, first you understand the manual procedure for column design. Later you can watch the video on design of columns on ETAP software. So from ETAPs you extract P, M2, M3 values and you start calculating it. So you will came to know what is the design procedure. So mainly column design includes two steps. One is calculating the design moments and calculating column capacities. So in this lecture I covered these two steps. One is calculating moments, design moments, and calculating column capacities.